Wow. There's only two people, Namrata and Matt. Okay, well, you guys can switch on your cameras. Well, I think other people will be joining us. If not, we'll just do a class with two students. That's fine with me. It may be fun too. And the guys who are not coming to class habitually, meaning like 4 or 5 times at least, they've just been absent without reason. They're probably not even going to get a B plus, so they should know, right? And so there's the reason I'm saying this is because sometimes students email me when the grades are out. Say, hey, why did I get this grade? And so on. And so this is the reason I have to mention this now, so people keep this in mind. Karthik, yeah, welcome to class. So what is it that we were planning to do today? We were planning to do pointers, yes? Yeah. So yeah, we can do pointers and stacks. Yeah, we were going to do stacks also, stacks and pointers together. So we'll implement stacks using pointers. And I think that would be fun. We don't have to start right now, of course. We'll start at 8:10. Maybe a few more people will join. And I don't know, when do the UCs, when does the spring quarter end for UCs? Different UCs end at different times. Hey, and Namrata, you're at a UC, right? Do the different UCs have different times when the...
I think only two UCs are in semester system, but I'm not sure about them, but everyone else who's on quarter system, this is week 9, so week 10 next week, and then there's finals week. So I think.
Oh, so week 11 is a finals week for UC.
Yeah.
UC.
So break starts on the 27th. Is like that 27th week is break, March 27th.
I see. Okay. Yeah. So our final week is, final exam is on the 30th or something. So it's quite. So you have a whole week to study for our final after UCs. Okay. All right. How about you guys just talk amongst yourself, Elijah, Matt, Hannah, Karthik, and Namrata for about 10 minutes, 5 minutes. Okay, 5 minutes. We'll start at 8:10. Is that okay with you guys? Yeah. Hey, Karthik, you're at a UC too, right?
Yeah.
Are you in the same? Are you in the same UC as Namrata?
I don't know which UC is she in.
I'm at UCSC.
Oh yeah, same.
Oh, okay.
See, you guys are the same college. You don't know each other. That is so funny. But maybe different majors.
Which college?
College 9.
Ah, makes sense.
Where are you?
Oh yeah. So different.
Merrill.
Different. There's a Cowell College there too, right? Cowell College.
Yeah. There's different sub colleges. It's a whole thing.
I remember driving through the campus one time when my kids were younger, and there was Cowell College. So, yeah, nice, very scenic place. Yeah. Anyway, okay, all right. So you guys talk, okay? But what are your majors? Karthik, what is your major?
I'm a political science major.
Oh, so you're not even in. You're not a.
Yeah, I'm not even. I'm doing. I mean, I'm taking this class partially for a math G and just to get a feel for CS, because literally all of my friends are CS majors, and I have no idea what they're talking about half the time.
Yeah, okay. All right. Well, do you think this has helped you? This class has helped you?
Oh yeah. Just a lot. I finally understand what computer science is.
You can butt into that conversations and say, hey,
hello. I know what Stack Overflow is. I understand why you guys hate C++. I get it.
No, that you should say that. You say, hey, you guys are wrong.
Well, I understand why it's difficult.
Not linear. That's exponential. What you say is now log linear, not linear. Yeah. Yeah, that would really be cool. All right. But Namrata, you're doing computer science, yes?
Yeah, I'm a computer science major.
Great. Yeah. I think there's a whole bunch of people from UCSC from last quarter too. They seem to be enrolling in this class. And I think Andrew Richmond is I think he's doing CS at UCSC. He was in my 2A. He's doing my 2B now, and he says UCSC has a track for game development. Yeah, and he's interested in getting into that. So this is lots of exciting options out there. So I'm glad you guys are having a fun time and also picking up stuff that would help you. When you go ahead and especially when if you plan to do graduate courses and all, picking up good practices early on helps you in your graduate course. Because I know a lot of students, when they do graduate courses, the first year even for some of them is really, really hard, because I don't know, maybe, yeah, because just because they had failed to invest the time during the beginning things, and it actually makes a difference, for PhDs and all, it makes a difference whether you complete 6 months earlier or 6 months later, and the initial part actually makes a huge difference. All right. Okay. Anyway, it looks like most of the regulars are here. A few people are missing. You guys have somehow got to reach out to them through your student network, Discord, and all these other things. Tell them, hey, you guys are missing out not only on the material that we're talking about in class, but also points. I mean, I can't understand why are people, maybe they're not really interested in the grade too. That's possible. Okay. So if they're not interested in the grade, they should certainly be coming to classes and picking up the material. So I don't know why they would not be picking up the material as well as being absent. So you guys have to tell them. Okay. Foothill has an email. Yeah. Okay. Nothing important. Okay. All right. Good. All right. So who wants to code today? All right. Every one of you has coded, but if you want to, this would be a great opportunity. Also, we'll code with pointers today. Okay, we'll code with pointers, and try and implement a stack using pointers. I did this already. I think the previous quarter we did it once. So I'm pretty confident we'll get through it very quickly, and then we'll have an opportunity to play with what we've created and stuff. Okay, so who wants to code? Today. Matt, yes, thank you. Hey, first person to, yeah, I don't know if you raise your hand to say
I
yes
just
or
need
maybe.
30 seconds to.
Yeah, sure. Okay, cool. This is so cool. Back in the day, when I was teaching in a class, I used to have to do all the coding. I used to be up front and, my laptop open and coding. I code the same thing, quarter after quarter. It starts getting boring. Well, not exactly the same thing, obviously, but still, I started to get the feeling that I was really taking away the interesting part for students. Because coding is really interesting. Why else would you enroll in computer science? I want to code. I want to learn a code. And then you say, all right, come here, but you're not going to code. I'm going to code. You can watch me code. That's, that is like, you buy the ticket to the movie, but I'm going to go in and watch the film and come back and tell you the story, right? Nobody wants to do that. And so I think this is working out much better. Also, I think it's better for students to watch other students code rather than students to watch the professor code. Because if the professor codes, I think the students automatically say, well, it's probably the same as in the textbook or the modules. I can read it later, so you can switch it off. But if another student codes, I think there's probably some kind of an extra motivation saying, hey, you know what? Maybe that student may make some mistakes that I could also make. So let me watch closely, right? So I think students coding much better. Well, while Matt is getting ready, if you guys have any questions, or even if you have any specific topics that you want to talk about, right, you can ask, and then once Matt starts coding, we'll, try and link the topics that you bring up into what we're implementing, so that you'll have, yeah. Is this a private window, by the way, Matt?
I think so.
Okay. All right. Well, I don't know. Right now, it's okay. I think you don't have any private material on. So dismiss the blue panel, delete everything, and we'll start with a screen, a clean slate as usual, and dismiss the blue panel so we have the whole screen. Yeah, the blue panel on the left, you can dismiss it by clicking the less than sign in the middle of the screen.
Oh, okay.
All right. So yeah, put a comment saying today's date and say today we will play with pointers and dynamic memory and implement a stack abstract data type while we're at it. I think, yeah, play with pointers and dynamic memory. And within parentheses, you can say heap, right? Heap, yeah, because dynamic memory is heap memory. Non-dynamic memory, automatic memory, is in the stack that's given to you by by the system. Play with pointers and also implement a stack and also implement, yeah, thank you, yeah, and also implement a stack abstract data type. Yeah, abstract data type, not type def type. That's all. That's all, and then we can go ahead and implement it. But before we get into the before we actually implement the stack data type, let's do a main and just play around with pointers just to get a feel for what pointers are, things like that. Yeah, right. So yeah, int main. There you go. Thanks. Yeah, and also put in the hash includes at the top. I think we need IO stream at the very least. Hash include IO stream. And then you can yeah, use within angle brackets. IO stream has to be within angle brackets. Yeah, and then a blank line after that, and you can say name using namespace standard. Okay, all right. So what is it? First of all, a pointer is nothing but a memory address. That's all. Okay. So as far as a memory address goes, it is just a number. Okay. Think about it. A pointer is actually one of the simplest data types. It is like a primitive integer, character, anything else, right? Whereas you have more complex objects. You have a string. A string is a complex object because a string is not a single. A string is a package which contains an array of characters inside it. It contains the length of the string. It contains a whole lot of metadata information about the string that will be useful for methods that access the string, saying, here's my string. What is the length of the string? It doesn't have to go into the array and count all the characters. It's already stored as a number. It'll just say, hey, that's your. So that's why ask a dot length of a string is really fast. It gives you the number like that. But string is a non-trivial data type. Okay, I don't want to say complex. It's because a simple one, but it's non-trivial. It's a non-trivial data type. Whereas a pointer is actually a trivial data type. Therefore, I think working with, or at least understanding what a pointer is should, in theory, be a whole lot easier. Okay, whole lot easier than understanding most of the other data types, because pointers don't have methods attached to them. If you want to understand a string, you need to know, well, the string is that. You cannot do certain things with a string. Yeah, okay, you cannot do certain things with a pointer too. But then a string also has methods like length, substring, all these, append. These methods you have to understand with a string, but with pointers, there's nothing like that. It is just a memory address, and as far as a memory address goes, it's just a number. So it's like saying, which room is the professor located in on campus, right? And you can basically say, yeah, with that room number is 4218. Is it 4218? It's been such a long time since. I actually exchanged offices with Rosa at one point, and then I exchanged back with her last year. So I should be back in 4218. 4128 or 4218, right? So, but you look at it, it's just 4218. It's a number. And it could, and you could basically say, you can say, what is, how many people are enrolled in spring 2023? 4218 or 4230. That's a number. So you can add one to it, subtract one to it from it. It behaves just like a number. A pointer is also just a number. However, right, when you add one to a pointer and subtract one to a pointer, it behaves very slightly differently, and you'll get to know, right? We'll find out. Okay, so how about we find out what a pointer is. So let's declare an integer, right? So say int n. These are going to be experiments, okay? We're going to be experimenting with n, right? Int n. No. We just say int space n. Yeah, int space n. No ampersand there, okay? Because if you say ampersand, that means n is a reference to an integer. That the other integer has to exist somewhere, and this integer n is just a reference to that other. It's an alias. If you have an ampersand in front, it means that that's an alias. That means there's already a variable. This is another name for the same variable. That's what it means. Yeah. So on your Mac, you create shortcuts for files. You have a file, and then you can create a option, click and drag, or something like that. You create a shortcut. Yes. I think on Windows it's called alias. It's a long time since I used Windows. On Windows, you can create an alias for a file. Yes or no? Are there any Windows users here? Nobody. Hey, everybody's using a Mac. Oh, Namrata, is there something called an alias? A shortcut? It's called a shortcut, isn't it? You can create a shortcut for a folder or a file on Windows. Yeah, and I think on Mac it's called something else. Or maybe it's called a shortcut on Mac too. Right. Okay, so it just like a shortcut, it's an alias. If you have, we'll find out. Okay. All right. So int n. Oh, not and n. Yeah. And let's give it a value. Well, let's not give it a value right now. Put a semicolon. There. Okay. Now one more blank line. I put a comment there. Right. And start a comment. And let's say where in the world is n located? Okay, like where's Wally, right? So where in the world is n located? Okay, what is the address of n? What is the address of n? That's exactly what we're asking. So yes, we can. So on the next line, yeah, what is the memory address of n? Memory address. You say memory address. It's clearer. We're making all these accommodations for students who are not attending class, okay? So you're putting comments in the code so that, students who are not in class can read it and still understand what we're doing. That's, they should attend class and find out. That's better. Okay, all right. All right, so on the next line, immediately after the comment, let's just say, here's the answer, right? So we say C out, left shift, right? And then within quotes, say n is located at memory address. Within quotes, you say, within quotes, n, no, lowercase n, because it's our, yeah, thank you. N is located at memory address, space, and then outside of the quote, get outside the quote, yeah, and then left shift. No, you don't need the semicolon there, yeah, right. Space, left shift. Left shift is 2 less than signs. Yeah, right, space. Now, how do you get the address of n? Where is n stored? And C++ gives you such a simple and easy way to find where the address of n is. All you need to do is just stick the ampersand in front of n and you get the address of n. It's not n anymore, right? So say ampersand n, which is what, Matt tried to do there. It has slightly different meaning there. If you put it on the declaration line, it says n is a reference. But if you put it in a place where n is being accessed, it means it's the address of n, right? So you have to say ampersand n. Okay, ampersand is a shift 7 n, right? And then left shift and L. Right. So if you run it now, you will get a huge hexadecimal number. Okay, a hexadecimal number starts with 0x, maybe, I don't know. It's and that is actually run it. So you have to select the language. Select the language C++. I thought you already had that language selected when you got in here. No, you got to select the on the right. You see on the right of the window. You see select. Yeah, select C++. Yeah. All right. So if you run it now. Oh, it actually did run, right? So you see that big number there? That big number in hexadecimal is in fact the memory address. In fact, copy that and open another tab. Copy that memory address alone. Right? Now open another tab and go to Google and say convert from hexadecimal to decimal, right? Convert from hexadecimal, and just say paste it, just hex. Convert from hex. Yeah. No. Just convert from hex and then paste your number. Right. So it'll tell you what the number is. It didn't. Wow. I thought I did it. That's interesting. You know what? Let's try Bing. Try Bing. Because I read something on in the news recently that said Bing would try their own chat. AI hex. Yeah, and then put your number there. Yeah, try that. Yeah. Okay. So this is doing the reasonable thing. It recognized that you want to convert it, and so that number there, 10 to the 14. Wow. So let's make that 10 to the no. That's okay. 10 to the 14. That would be if I took away 6 from there, that would be megabytes. That would be 9. 10 to 14 minus 6 is 8. Right. So it would be 8 is already 100 million. 100 million. So 100. So you have wow, that seems to be a lot of memory. How much memory do you have on your computer, Matt?
I don't know, 16 gigs maybe.
No, I think 16 gig is 16 billion, isn't it? Oh no, 16 billion. See, it's only 16 billion. But this value here is more than 16 billion, isn't it? 16 billion is 16 times 10 to the 9, isn't it? 16 is it 16 billion is 16 times 10 to the 9, isn't it?
Yeah, I think so. Yeah.
Right. Whereas this is saying that n is being stored as at a location, which is whose address is what times 10 to the 9. This is actually 14072. That's 14,000 gigabytes. How could you have 14,000 gigabytes? Something is wrong here. All right. So here is a puzzle for some of you to figure out and post in the forums. Okay. Maybe you can take a screenshot of this. Well, you don't have to take a screenshot. It's there in the code. You got to say, let's go back to the code. Okay, you copy that number. 1.47. 1.407. Go back to your tab. Go back to the other tab. Go back to the other tab. Copy that big number. Just that. Yeah. Copy that and go back to your code now. And so this and you can say the code prints that. The code prints that thing. The code prints this, which is and on the end, which is 1 times 10 to the 14. No, 10. No, not 10. 14. 10. Put a caret sign between the 10 and the 14. Right. 10 up arrow 14. 10, 10, not 1 to the 14. 10 to the 14. Right. Which is also which is also simplifying on the next line. You can say on the next line simplifying, that should be 14072 14073 40723 times 10 to the 9. Yes, 9. So a megabyte is 10 to the 6. A megabyte is 10 to the 6. Someone should correct me if I'm wrong. A megabyte is 10 to the 6, isn't it? A million is 1 megabyte. How come everybody is quiet? Because these are simple questions. You guys should feel free to answer these things. Isn't a megabyte one? Yeah, a megabyte is 1 million bytes. 10 to the 4.
It is 10 to the 6.
Yeah, 10 to the 6. Therefore, if you have 10 to the 9, that's a gigabyte. So 10 to the 9 is 1 gigabyte, isn't it? Okay, so here so the system is telling us that this n, which is totally surprising to me, right? I totally did not expect this, right? This is telling me that what we ran now, this experiment is telling us that this machine has, oh, this is not your personal machine. We're an online GDB. We're an online GDB, right?
Oh, yes.
Okay. Yeah. Maybe that explains it, because that is basically saying this computer on which you're running this small snippet of code has 14,000 gigabytes, 14,000 gigabytes, which is what is after gigabytes? Is it petabytes? Terabytes. This is 14 terabytes of memory, right? So that's 14 terabytes of memory. So which is so that this machine probably has 14 terabytes of memory. Online GDB. Why? How is that possible? Maybe it's a Docker. Yeah, maybe. Yeah. Okay. Maybe it's running in a Docker container. All right. This is my hypothesis. Okay, it's running in a container, which is a part of a gigantic machine, which is running many containers. Each one of them is gives the illusion of having your own computer, essentially, right? And however, it says, your memory segment starts here. Your memory segment starts here. So it's taking that huge memory, chopping it up, and saying your memory. And I think that's what's going on. If you run the same memory, this same program on your Mac, right? Just Command A and copy the whole thing. Command A and copy the whole thing. Yeah, have you copied? Now,
Yep.
Start a terminal on your Mac. Start a terminal on your Mac. Do you know how to start a terminal on your Mac?
Yep.
Yeah. Start a terminal and also share the terminal if possible.
That's the terminal.
Yeah,
Right?
hit command plus a few times.
Command plus.
Yeah, command plus. Well, a few more. That's enough. Okay, good. No, that's it's fine. Okay. Now, type what I say. Cat C. Oh no, you can't paste it like that. Hit Control C. Hit Control C. Control C. Control C.
It doesn't work. Control C.
No,
Oh.
I'm pretty sure.
Okay. Yep.
So type cat greater than. By the way, I don't want to litter up your Mac, right? So before you type cat, so go to the beginning of the line again. Say CD/temp, right? CD space /temp, and get rid of the cat greater than, and get rid of the cat.
CD
and then you need it's CD space /tmp. What that says is that change my directory into the system's temporary directory, because I'm going to create some files. I don't want it littering my desktop or my home directory. I don't want, because we're going to create a file there and compile and run it. You don't want it to clutter up your desktop, right? You don't want to clutter because you'll forget about it later on, and then it'll be there and you don't know whether to delete it later. Okay, so we're saying just go into that temporary directory. We'll create some junk there. You can feel absolutely free to create any junk you want in that directory, because anyone can. The /temp on Mac, many computers, okay, is a special directory which allows any person to create anything there. However, you cannot touch someone else's file. So if both Erica and Mac create files in /temp, they will have access to their own files. They can delete it, but they can't access other people's files. So it's very nice. And the nice thing about creating files here that you are not sure you need forever is that the system automatically clears things out in /temp. Every time the system is rebooted, temp is cleared out. So you don't have to worry saying, oh, I left some, trash there. And it's like going into the trash can and doing stuff there. You don't need to clear up, right? So if you have a huge trash can and go and do stuff there, you can be as untidy as you want. Well, it's not going to help you, but you don't have to clean up afterwards. So /temp is your trash can, the system trash can. Not real trash can, but it'll get cleaned up automatically. Right. So hit enter. Now you're in the /temp directory. Hit enter. All right. So that's it tells you, the prompt tells you that's where you are. Okay. Now you say cat greater than, cat space greater than. Yeah, that's fine too. Right. And then say experiment expt.cpp, right? expt experiment, right? expt.cpp. So what we're doing there is we're going to create a file called expt.cpp, which contains the code that Mac copied from online GDB. And what I'm doing there you go. Mac, hit enter one more time. Now hit Control D.
Control T. Oh, D.
D. All right. Okay. Control D is a signal to Unix and Unix-like systems. Mac is also a Unix-like system. On Windows, it's Control Z, by the way. Okay. So it says Control D means No more. It's Control D is synonymous with end of file. Now, what that command does, it's a Unix command, it's a Linux command. You don't need to know that for CS2A, but it's actually very useful to know, right? So cat is basically a command that that takes an argument and type cat, type space cat, type cat space, and what was the file we created? expt.cpp, expt.cpp, expt.cpp. Right now, it'll dump the contents of the file. That file exists and has what Matt just stuck in it, right? So if you hit enter, you'll see the contents that went into the file. There you go. You saw that? So everything that Matt pasted went into the file. You do an ls as list all the list the file, ls space -l, right? -l, and then space, and then type ex and then hit tab, ex and hit tab. Tab will autocomplete. Hit tab, right? So auto completes. That means that file exists in the /temp directory. Now hit enter, it'll tell you the details about the file, how big the file is. There you go, right? This file, expt.cpp, was created by Matthew Locke, right? Wheel is, ignore wheel. Wheel is just a group name. He's, the operating system sticks you in a group of people called wheel. Okay, so don't worry about that now. This file has 461 bytes in it. Let's say this file has exactly 461 bytes, which means that this file occupies, when you load it into memory, this file will occupy 461 times 8 bits, individual bits in memory. That's all, right? So exactly. So 461 bytes. It was created on March 9th. Isn't March 9 today?
Yes.
Yeah. Why is it 11:32? Why does it say 11:32? Your computer in a different time zone?
In the East Coast.
Are you right now in the East Coast?
Yes, I'm in Boston.
Oh, wow, I had no idea. All right, okay. Yeah, okay. All right, so yeah, there you go. So it was created at 11:32, and the file is called expd, and this file is 461 characters big. So that's how many characters are there. Okay. Oh, and on the very left, you see the permissions of the file. The RW. So the first is a dash. It could be a D or an F or something else. It's a dash. That means it's a regular file. It's just it's a regular file. And after that, R means this file is readable by the owner of the file, which means Matthew is the owner. He can read the file. W after that says the owner of the file can write into the file too. So Matthew can write into the file. Okay. And then the next dash, ignore it because it stands for executable. Executable files. Don't worry about it now. But after that, you see another R. Okay. That means people who belong to the group wheel, right? Same group as you, can also read the file, but they can't do anything else because the W is missing for them, right? And the last 3 letters are for the whole world. Everybody else in the whole world can read your file because it says R for the whole world, right? But nobody else can write the file or execute the file because the remaining 2 are dashes. Okay, that's what it means. It's basically just Unix how-tos. So we don't need to know this. Now we're going to compile this program and run it, and we'll see where the address of n is on Matt's machine. Okay, so to compile it, say type G++ and hit enter. Well, let's see if you have G++ first. G++, hit enter. No, G++. Yeah. Oh, it is there. Okay, Control C, Control C, Control C. All right. Okay, so type G++. G++. Type G++ again. Right, and now space with the file that we want to compile is expt.cc, right? Exp. You can just hit tab, it'll autocomplete. Yeah, right. No. All right, okay. Right. If you do that, what happens is that it will compile the file and produce the output as usual, but it won't produce the output and put it in a file that of your choosing. It'll just put it in a random file, not a random file. It'll put it in a file called a.out. Most people don't know. So if you do ls-l of a.out, you go back to the beginning of the line and type ls space -l. Well, actually, why don't you just hit enter? Because you'll see all of the files in the temp directory, right? There you go. You see that file called a.out? That was just created by you. Look at that. It was created by Matthew at 11:36, right? That was just now, 11:36. But Matt, how did you create? You don't remember creating a.out, but you ran the compiler. Yes, the G++ command. The G++ command created a.out, but the file that G++ created is owned by you because you're the one who started G++. Does that make sense?
Yeah.
Okay, right. So now that file is the compiled version of expt.cpp. Now, however, let's not run that file, right? We'll create our own. So up arrow a couple of times, up arrow. One more. Yeah, all right. Now space, dash O, EXPT, right? Space, EXPT, right? Now what that says is that compile the file, but don't take the output compiled file and put it in some, a.out file, put it in a file called EXPT. So now it's going to create a file. The output file is going to be called EXPT. So if you hit enter now and do an ls-l, right? Now, if you do an ls-l, you'll see an identical file, right? Identical file. See that expt.cpp. There you go. It is identical. It is exactly the same as a.out, except it's called EXPT. In fact, you can confirm that it's exactly the same as a.out by saying diff, diff. Yeah, no, the bytes, the size of the files could be the same, but how do you know inside the file it's the same, right? Diff will go inside the file and check it byte for byte. Hey, the first byte is the same, second byte is the same. It'll tell you if it's exactly the same, right? So a diff space EXPT space a dot, and then hit tab, it'll do a dot out, right? Space a dot, and also hit Control L, it'll clear out the screen. Control L once, Control L. Right now, if you hit enter, diff will tell you it's exactly the same, or it won't say anything at all, right? You hit enter, right? It doesn't say anything. Now, that is one of the really cool things about Unix, the Unix operating system, is that when you run a command and it produces no output at all, that means everything was, hunky-dory and correct. Okay, so there used to be a standing joke, and well, not a standing joke. There used to be a famous saying in Unix, saying no news is good news, meaning that if you don't hear anything back from the operating system, it did its job. Okay, which means that the developers of the operating system were so confident that it's a kick-ass operating system, will always do the right thing, that if it does the right thing, it won't tell you anything, right? It'll only tell you things if it goes wrong, right? So if you say, for example, do an ls-l again, ls-l, up arrow until you get ls-l. I think you have a couple, yeah. Right, hit enter. Let's pick two files that are different. Expt.cpp. Here you compare expt.cpp and PowerLog. Okay. Yeah, diff expt.cpp and PowerLog. It'll tell you, wow, this is a whole lot of difference between these two files. Yeah, hit enter. Oh, it's a directory. Oh no, wait a sec. It's a directory. Want to find a text file? No, it's just there. PowerLog /PowerLog. Hit p tab. No, P tab. Yeah, tab. And then hit tab one more time. It'll tell you some files in there. It'll tell you what files exist in that directory. Tab one more time. Nothing?
It's nothing. Yeah.
Oh, it's an empty directory. All right. What about, yeah, maybe that com.google.keystone, right? Maybe that is a text file, right? So type com. I'm just looking for just any other text file so we can compare the two. Yeah, Keystone. Oh, is that a directory too? They're all directories. Well, why don't we create our own text file? Okay, so go to the beginning of the line. And say SEQ, right? SEQ, and hit enter. Oh no, SEQ space 10. SEQ space 10, and hit enter. SEQ is a built-in command in Unix, like operating systems. It's a sequence generator. So if you want a sequence of 15 numbers, you say sequence SEQ 15, and it'll give you bam, you have a list of 15 numbers right there. Okay, so we got the first 10 numbers. Let's take those 10 numbers and stick them in a file. Okay, so up arrow one more time. Right now, after the 10, put a greater than sign. Right there you go. Yeah. Greater than, and say 10.txt, ten.txt. Now it's gonna, the output of that command, whatever it produced on the screen, is not going to just go to the screen. It is now going to go into 10.txt. Right. So if you hit enter now, now you do ls-l, you'll see a file called 10.txt right there. There you go, 10.txt, and it has exactly those 10 characters that, the 10 lines that Matthew generated. In fact, if you do cat 10.txt, you'll see what your cat 10.txt, you'll see that. You'll see, right? Right? Now you can do a diff of 10.txt and that other file, expd. Right? 10.txt and expd, it'll tell you, right? Line for line, every line is different, right? So yeah, there you go. There you go. You see, it says, the less than says, these lines are different. In this file, less than means the first file, greater than means the other file. In fact, if you want to see the kind of output that comes from Eliza, one of those quests that I use. You'll see this, right? Go up arrow. One more time. All right, go to the beginning of the line. Up arrow, that diff command. Down arrow. Do down. Yeah, right. Now hit Control A. Control A takes you to the beginning of the line. Right, now type S, the little S. So sdiff is another command, free. So when you get a Mac or Unix or any computer, you all automatically get a whole bunch of commands that have already been created there for you to run. Okay, it's freebie commands. Sdiff is another command. It's a whole bunch of commands. It's worthwhile getting to know. Right? Sdiff is another command which does the same thing as diff, but basically presents the output in a slightly more user-friendly way, side by side. Okay, which is what you'll see. Now, if you hit enter now, you'll see the kind of difference that you see in our quest. This is what you see in our questing system. When you generate an output and say, hey, it's different from what I expected. Here you are. Okay, that's what happens. See, the vertical bar says completely different. Okay, and then if it greater than means, oh, this line exists in this file, doesn't exist in that file. Right, so this is what sdiff is. In fact, if you want to know what sdiff does, you just go to a browser and say man sdiff or manual page for sdiff. You know, go back to your right. Well, all right. No, let's run the command. Let's run the command, and we'll go back. Okay, so run the command expt, and it'll tell you what the address of n is, and we'll see. You know, yeah, expt, pt, expt. That's the file that we created. Yes, yeah. Hit enter. Oh, you got to say /expt because the current directory is not in your path, where your path is the place where you can find executable files. It's not, the current directory is not there. Okay, yeah, there you go. Enter. Yeah, can you convert that number also from hexadecimal to decimal? I don't know. This also looks like a big ass number, but no, I think it's smaller. Okay, yeah, can convert that number. Go to your browser and convert that to decimal. You can share your browser screen too now, I think. Yeah, I think Bing was converting. Bing, yeah. Oh, you can just say yeah, yeah. You can just hit enter. We'll see if it converts it. Just hit enter right there. No, it still doesn't. Yeah. Oh, this is Bing. Okay. Well, Bing and they're very similar to each other now. I can't tell. It is still 10 to the 14. So I don't know what's going on here. Okay, you guys have to figure out, maybe even ask on Stack Overflow. You only have 16 megabytes, 16 gig of RAM, but it's telling you that it has 14 terabytes of RAM, according to this. Or the address, the memory address of N is so far out. Why is it so far out when you don't have that much memory? Okay, but anyway, I don't know why. You guys can research this and share, because I would also be interested to know, right? Because I've got to go and look and say, hey, why the hell is this happening? It's really strange. But anyway, this is what it is. N is stored in memory, and the memory address is that. And what that number means is that the memory address 0 is off limits. Okay, the CPU, the C++ language says you cannot put anything in memory address 0, so it's a reserved address. So the first byte, the very first byte on your memory chip, right, is actually memory address 1. And so the next byte is memory address 2. And so you keep doing that 14 billion times. That's where N is stored, right? The N is, and you have exact access to that place. And so if you want to change the value of N, you can do it in 2 ways. You can actually say, here you can all right, so let's print what so what does N contain? We said on line 10, Matt said int N, yeah, but it didn't say int N equals 5, and it didn't say N equals this value. It just says int N, right? N didn't get initialized. It could be any value. So the compiler could have said, I'm going to initialize it with 0, but you don't know. You never take it for granted. Okay, even if you get 0, so in fact you say cout n after line 17, yeah, just say cout n, n equals, yeah, cout, and say within quotes you can say n equals, and then actually n itself. Within quotes you got to say n equals, yeah, space equals, and then left shift n itself, and then endl. And you probably will get, no, you need the end line, right? If you run it now, you'll probably get some junk value, right? Or 0 if the compiler had initialized it for you. It is 0, the compiler initialized it, but I usually tell it's not initializing to 0 for integers is not guaranteed by the C++ standard, is what we found. Okay, in CS2B and CS2C, when people were coding and something was not initialized, they just assumed it was initialized, was not initialized, the program didn't work. That's when we actually found it doesn't get initialized by default. It's happening here by chance. We can't take anything for chance in computer science. Okay, like magicians, where magicians never do a trick that will succeed 99% of the time. They'll only do tricks that succeed 100% of the time, for sure. Like that in programming, you don't take chances and say, hey, your program worked a few times, I'm gonna let it loose in the wild. So so that's why initializing variables, you don't say, oh, it seems to be initializing. No, you have to. So go to the line 10, and where you say,
so the memory address changed?
no, the memory address didn't change. No, we're saying what is contained in that memory address is what we're saying, right? N is the value of n is what is contained in that memory address. Previously, we printed the memory address of n. Yeah.
Yeah.
Now you're saying that memory address contains this value. So that memory address contains the value 0 right now. In fact, go to line 10. I'll show you, right? Go to line 10 and then say n equals 5, right? N equals 5. Right now, if you run it now, it'll say n equals 5. Yes, because that memory address contains 5. Now there is actually how can we do this? Okay, what is a memory address? How do we actually see? Run it one more time. I want to see if it's exactly the same. All right, it ends in 3b4. Okay, run it one more time. Run it one more time.
Yeah, it's changing.
Yeah, it's changing because your computer is running many tasks, right? It's in the background, it's running tasks, so memory is getting allocated in different places, it's getting shuffled around. So I was thinking, if it's always going to the same place, we can actually go directly to that memory address and see what's in there. Now, it is possible to do if you're in Xcode. If you're in Xcode, for example, are you comfortable with Xcode?
Yeah, I use Xcode.
Yeah, why don't you get into Xcode and put the same program in Xcode? Put the same program in Xcode. By the way, before you do that, let me check. Okay, do you want to do this, right? Everybody, what I'm planning to do is, if you go into Xcode, compile this program and run it, we can put a breakpoint, right, in the debugger and say stop here. And at this point, you can actually get to examine the complete memory of the computer. You can say, right, I've stopped my program. The program is running. And I've frozen the program in its tracks. It's running and stopped right now. Now I can look at all the memory locations on my computer. Xcode will let you go directly to that memory location. Say, what is in that memory location? And you can see that that memory location contains the value 5, right? How incredibly cool is that, right? This is billions and billions of memory locations. And one of those locations contains the value 5. And even more incredible is that you have the power to directly access that byte. Out of billions and billions of bytes, you can access that byte in nanoseconds. Or milliseconds. That location out of billions and billions, I want to change from 5 to 6. You can do that. I was going to show that to you, but if you're not, if that's slightly, digressing from what I wanted to talk about today, which is pointers and all. So I don't know if it'll help. If it'll help, let me know. We can go down that path. But this is basically it. Okay. So n equals 5, and address of n gives you that thing. Now let's create on the next line, after n equals 10, right. So let's do what Matt did first. So yeah, on the next line, right, say int ampersand m, right? Int ampersand m, ampersand, shift 7, m equals n, okay? N. Right now, and then triple click on line 14. Yeah, and paste it one more time under it. So Command C and then 2 Command V's. Command C and 2 Command V's. Yeah. Right now, say instead of n is located at, you say m is located at. Right now, let's run it. You know, in fact, this is going to be an experiment that, all right, let's run it now. All right, so what's going on? You have two variables, but they're both stored at the same address, isn't it? Is it the same address? I can't see clearly. Maybe I can change the
Yeah.
glasses.
Yeah, it's the same.
It's the same, isn't it? There's two different things which are basically stored in the same location, exactly the same location. So that is what a reference variable is. A reference variable is just a different name, but it's pointing to the same place. So we talked about reference variables before, right? Reference. A reference variable is exactly the same thing, but it's pointing to the same location. Right? It just has a different name. So like a rose by any other name smells as sweet or something like that, you know, Shakespeare, right? So it's two different things, exactly the same thing. That is a reference. So the ampersand is an alias there. Does it make sense? Now, if you, in fact, if you go on hit enter on line 21, hit enter on line 21. Yeah. Now say M++, hit M, say M++. Yeah. You know, and what you did was right. M. Maybe I should have used A and B, you know, less confusable, A and B than M and N, right? Semicolon. Now, semicolon there. And now copy and paste line 21. Copy line 21. Copy line 21. And then paste it under that. Now you see that you didn't change N at all, right? You didn't change N. You only changed M. But now run it and let's see what happens. There you go, right? You didn't change N at all, but N changed. N became 6. Why? Because you said, you know, M is also N, right? M is an alias for N. You change M, N also changes. Does it make sense? It's actually a very powerful little experiment because this would also, you know, play into what you may see in your exams and all. That's what the reference variable is. A reference is exactly the same. It's an alias. So you can use either from that point onwards. Now, if there's uses for reference variables, you'll find out, you know, when you have to use a reference variable, you'll find out. Okay, so now let's see. All right, so now this N was stored on your stack, right? So it's a local variable. It's stored in your stack. Now, a stack, like we talked about stacks last class, you get a fixed amount of stack. Every program when it starts, get a fixed amount of stack. It's like 100 megabytes. I don't know, something like that. Okay, but your computer has 16 gigabytes, lots and lots of RAM. By the way, someone has to figure out why, you know, the address is so big, because even though he has only 16 gigabytes, it said N is stored at that location. That's like 14,000 gigabytes. You know, that location is really big, isn't it? That number was really big, wasn't it?
Yeah.
Yeah, so it actually may be worth a question. So one of you could ask on Stack Overflow, saying, hey, I was trying to, my computer only has 16 gigabytes of RAM, but I tried to find the address of this variable and it's, you know, out there, out in the boondocks, like, you know, 14,000 gigabytes. So what's going on? I'm actually interested to know why that is. So see if you can find out. Maybe ask on Stack Overflow or something like that. Okay. Anyway, so that. Now, let's say we want N not to be stored in our stack, but actually on the heap, which means that even after my function, the function in which I'm using N is gone. My function has exited, right? Even because when everything that's on the stack, when a function exits, that stack is released, isn't it? That's why you know, when we talked about how a function is called, we talked about this before. So function A is running. All of A's local variables are on the stack here. Now A calls B. Now A's stack frame, one more stack frame has been pushed on top of that. Now this becomes, all of A's variables now become inaccessible because it's not on the top of the stack. The stack can only access the topmost element at any time. We're going to implement that very soon, right? So now that means this is now the active frame. One more function call, that's the active frame. So all local variables are in the stack. Now when a function exits, when a function says, I'm done, I'm returning to my caller, that entire stack frame is thrown away, which means all the local variables on the stack now disappear automatically for you. It's very useful because many times when we're programming, we want these variables to automatically come and go because we have, you know, this is my register, I'm working with these things. When I'm done, I'm going to go and then someone can come and take this entire disk and clear it off. That's your stack. So all the local variables, everything you're doing locally will be on the stack. When your function returns, that stack is cleared off for you automatically. And that saves a great deal of work. So the stack clearance happens automatically. However, that doesn't happen with a heap. The heap is massive memory, like 16 gigabytes out there. And if you ask for stuff from the heap, it is your responsibility to clear it up. Because otherwise, if you don't clear up stuff that you ask from the heap, you have what is called a memory leak. And if your program is a program that doesn't actually die, and is like, there are lots of programs that never die in the operating system too. They're called daemons. The program's always alive, and it's basically a program that reads your keyboard, for example, right? It's always there. As soon as you open the lid, it's there. It's reading your keyboard. And so those kinds of programs can't afford to have memory leaks, right? Because every time it goes into a loop, it's going to allocate one more byte. If it enters the loop 5 million times, there's 5 million bytes out there. And if it doesn't release those bytes, they're just locked up. The operating system takes that memory, allocates it to the program, and it will not allocate it to someone else and prevent other people from accessing it until this program actually dies. So if that program never dies, it's just going to eat up more and more memory and not release it back into the pool. And your program will start getting fatter and fatter. Other programs will start getting, resource crunch. They'll say, yeah, I've not enough memory for me. And then it'll start swapping, saying, oh, I'm going to take rearranging memory, and that's when your fan starts kicking in. So you see this effect, for example, when you have browsers like Chrome, for example, right? When you have Chrome and some of these browsers, good programs don't have this problem. Okay, good programs are nice and clean. But when a program has been around for a long time, even at places like Google and Microsoft, not everyone is a star programmer, right? You have star programmers, but you also have sloppy programmers who somehow manage to squeak into the company, right? Especially if you have 100,000 employees. There's going to be a good fraction of people that don't actually know what they're doing, but they'll probably know what they're doing, but they won't be experts. So they might write sloppy code, and that code might actually make it into a release product like Chrome. And that is why when you have a browser like Chrome and it's been running for 5 days, you'll see if you go into the task manager or on Windows, right? You'll see how much memory has been used by Chrome today, on Monday or Tuesday, right? Oh, it's my Chrome. I fired up my Chrome and it's using, let's say 500 megabytes of RAM. Okay, you come back tomorrow, it's using 600 megabytes, even though you have exactly one tab is open and it's just the Google homepage. It's still using 600 megabytes. And you say, hey, why is it using 100 megabytes more? Because some sloppy code in there, allocated memory, forgot to deallocate it. That's a memory leak. And so that's why browsers, you kill the browser, restart it, and you're back to your healthy thin browser. And this is the reason why badly written programs require, like if an operating system, right? If an operating system like Mac OS or Windows, that is badly written. That's it's because also Microsoft, it's a big company. There's lots of programmers. It's very hard to make sure that that's why there's huge attention given to Rust and all. Microsoft has this push for Rust, saying, oh, Rust is the language everybody should be using instead of C++, because Rust makes sure that you don't have memory leaks and things like that. It's memory safe and all. That's because when you have a big product, the chances of getting star programmers, rock star programmers only to work on that product is hard, isn't it? Because there's only a limited supply of rockstar programmers in the world. That's why you guys, if you master 2A, 2B, 2C, if you're going to really solid, you'll be in heavy demand because everybody wants rockstar programmers. It's hard to get rockstar programmers. If a product gets really big, you can only have a small set of rockstar programmers. Lots of people will be resource programmers, and bad code will eventually squeak in, I think, right? So, but it's very important to have an operating system like Windows be very squeaky clean and not have any leaky code. Because if you don't have that, your operating system itself will start getting fatter and fatter. It'll have memory loss, leakage. And then after a while, your computer itself starts getting slower because it doesn't have enough memory to go, right? And so you remember from bad old days of computer programming, of computers, you have to reboot your PC every few days, yes? Right now, this Mac, I haven't rebooted in, I don't know. I don't remember when I rebooted it last, right? But back in the day, I know, when I used to have these, ThinkPads and things like that, running earlier versions of Windows, I know these programs are getting fatter and fatter. All it needs is reboot the computer and it fixes it. Even yesterday, something happening on my iPad, not just right, okay. And then I Googled around saying, hey, how can I fix this problem on my iPad? And top answer for that is just reboot your iPad and it fixes, right? Which means that even on the iPad, there's some code that is basically leaking memory, or something is happening. It's locking up resources. When you kill the program and restart the operating system, everything is clean again. So that is a memory leak, and that is like the biggest problem. Now, just going to Java or Python does not fix the problem of memory leaks. Okay, people always think that, well, you know, C++, I could make these memory leak errors and I go, right? No. So what happens when you go to Java and other programming languages and carry a sloppy programming style? That's why I think that C++ is a good programming language for everybody to learn at the beginning, because after that, any other programming language you learn with proper discipline, right? In a disciplined way. But if you learn these other languages in disciplined way, right? Not having learned C++, or you'll program very sloppily and not cleanly, right? You'll ask for stuff and forget to give it back. And you'll use more resources than you need to. Your program will run slower. It'll do the job, but it'll do it slower. You heat up your computer, more CPU cycles, all kinds of bad things happen. And so where was I going with that? I know where I was going with that, but basically, you know, these memory leaks are like super duper important to nail down. Yeah, right. Disciplined programming. So when you learn this and you go into other languages, you program in a disciplined way. If you don't do it in Java, your program may not die. Okay, this is the thing. That's the thing, right? In Java and other places, if you have sloppy programs, your program may not die. But then, because, you know, even if you ask for memory and then don't give it back to the operating system, in fact, in Java and other languages, you don't actually explicitly release memory back to the operating system at all, right? It's only C++ that gives you the power to say, I'm done with this, take it back, operating system, right? You can give it to someone else. In other languages, you don't even have the power to do that. It is up to the operating system to do that. And the operating system employs something called a garbage collector. Okay, there is a thread called a garbage collector that is always running in the background, whether you like it or not. So there you go. Already your program is taking a hit. When you write something in Java, already some small fraction of the CPU, like 2%, is gone. You don't get 100% of the CPU in Java and Python, because that 2% of the CPU is now running what is called a garbage collector thread. Is saying, well, you know, is Matt allocating stuff and that he forgot to deallocate after he's gone, right? So it uses complex logic, sophisticated logic to figure out the things that Matt asked for from the heap but didn't give back, and then it takes that and cleans up after Matt for him. So these other languages have a servant, have a cleaner upper, okay, following programs around, saying sloppy programs, be sloppy, I'll clean up after you. Right? Well, you know, yeah, it'll work eventually, but that's not the way programming should be done, right? Programmers should be clean, do the nice job, and then don't bank on the operating system for cleaning up after you. Just like, you know, kids saying, I'm going to throw candy wrappers everywhere in my home. My mom and dad will come and pick it up after me. Okay, that'll only work as long as you're in your own home, right? After you go off to college and you live in your own home, you got to clean up after yourself. So it's better to learn how to be clean when you're at home, and so that's C++. So it'll teach you how to be clean. And learning to program clean is not just for writing efficient programs, it is also to make your own job easier as a programmer later on. People say, I need to write clean and efficient programs just because it needs to be clean and efficient. No, clean and efficient because your own job for debugging and cleaning up your debugging will be a whole lot easier if your program is cleaner. A lot of people just struggle with debugging because the programs are sloppy in the first place. And the garbage collector in Java and other languages, you'll actually see the effect, because you're running a program and it's just swimming along perfectly, and all of a sudden it grinds to a halt. I don't know if you've seen this in Java programs. You're running a program in Java and it's doing its job, and all of a sudden just freezes, and you think the program, you know, the computer has frozen, but you know, you go near to the system to take a look at, hey, why didn't my program freeze? And freezes all of a sudden. Have you had this experience? It seems to freeze. When you look closely, it's unfrozen and it's gone back. And so it's moving in spurts, like, you know, you're going and jam the brakes and go fast again, jam the brakes. Why? That unpredictability is because the operating system, or the runtime, Java runtime system, in all its wisdom, has decided now is the time for the garbage collector to go in and clean up. Okay, so you got lots and lots of litter in your program. All of a sudden, the garbage collector garbage collector kicks in, right, and says, okay, I'm going to clean up. And I'm freeze the program. I'm going to take all the trash and release it to the operating system and then give control back. That is what happens. It's jerky, right? Yeah. When you write programs in Java, you'll find out, right? And that is why trained C++ programmers who know computer science will be able to write Java and Python programs that don't have that effect. because they will write programs in which the litter is minimal, so the garbage collector does not have to kick in, without your willy-nilly, just like that, right? You don't have any expectation that it's going to kick in and kicks in. That only happens for bad programmers and bad programs, because they don't know. They got a lot of objects lying around. They don't know where they left, junk, and all of a sudden the operating system knows. They'll say, oh, there's too much junk, I'm going to clean up. So that kind of thing won't happen in C++. Does it make sense? That is why it is, I think, a good exercise to find out where memory is allocated and all. Now here in this case, we only allocated primitive integers. However, you can create a complex object, like we created a screen 2D object and all. So you can create big objects, and you can also say this big object does not need to be on the stack; it needs to be on the heap. So you can say, give me one of these objects, and it needs to live on the heap. Now, in this case, n is on the stack. Let's now create an n, another variable, right? So let's create an n. So go on to line 24. Actually, you can get rid of all of this. We can get rid of, should we get rid of all of this? Because, we want to keep this for the students who are not here. Put all of that in a comment block. Okay, so go to line 19, go to line 9 and hit enter. Yeah, hit enter. Now say / and a star, / and a star, star, right? Star. Now, and that is a comment block. Right now, and then go to line 24 and hit enter. Yeah. Now say star / star / right now, that means that entire thing is commented out. So far we're only familiar with the two / for starting a comment. That's called a line comment, inline comment. That comment is automatically ended when at the end of the line, whereas this kind of comment will only end when it sees the matching pair. That's a star, / star. Everything is commented until / again. So we are preserving that, and we'll put a comment. We'll put a comment there. Put a comment where you have your cursor. Start a comment. Above code. Put a comment there on line 26. And say above code fragment preserved for slacker students who are absent. All right. So above code fragment preserved in a comment. In a comment block for slacker students who are absent today. Okay. So now let's try another experiment below that. We'll say now we'll try the same thing with n. Now try the same thing again. But one more blank line and say experiment 2. One more blank line and say but put a blank line before that, and say experiment 2. You say experiment 2. Try the same line. No, you can have the blank line there because it's a new experiment, right? So you put there. So there you go. So you say experiment 2. We're going to try the same thing, except that n is not on the stack, but it is on the heap, right? Experiment 2. Try the same thing, except n is on the heap. Okay. So how do you do that? How do you ask the compiler to give you a location for storing an integer, but that should not be on the stack, it should be on the heap. And C++ gives you a very nice and easy way to do that. All you have to do is say int, right? Int space, now space. Now here's the thing, okay? You're going to say star p, okay? Int star p, right? Equals new int, right? Semicolon. Okay, semicolon, right? That is a magic statement there, right there, because that statement has a bunch of keywords. It has one keyword, new. New is a special keyword in C++. It says make a new object on the heap, not on the stack, on the heap, which means that after this function exits, after the function returns, that is still going to be there. It is up to me now to delete n. Okay, so yeah, right. So now on the next line, now let's do the same thing as let's say p equals, cout p equals. Yeah, within quotes, say p equals, within quotes. Yeah, p equals, and then the value of p itself. and then enter. Yeah, now if you run it, we'll see where the, that location is. It's still a big number. But you don't have to convert it and all. You know that it's a big number, right? So that is a memory address out there. And the operating system has taken 4 bytes, because an integer is 4 bytes, isn't it? An integer is 4 bytes. The operating system took 4 bytes starting at that location and says, hey, Matt asked for a new integer in the heap. So those 4 bytes now belong to Matt. It'll just mark those 4 bytes as owned by Matt, owned by Matt, owned by Matt, owned by Matt, owned by Matt. Okay, so nobody else can write into that. However, because it did that, now you have the onus of telling the operating system, I don't own it anymore. Because if you don't tell the operating system, I don't own it anymore, the operating system will never ever allocate it to anybody else. It's locked up. That's what I said by memory leak before. Okay, now print the contents of P, right? And also the other thing that I forgot to mention, in fact, we should do this. Okay, we should do this. No, we'll put one more comment on after line 29. Put one more comment after line 29. Right, the following statement, the meaning of the following, say the following statement means, the following statement means, and then colon space. All right, now here's the meaning of the following statement. Right, it says P is a memory address. P is a memory address. Star is an operator. Star is an operator that returns the contents of the memory address. Right, not the memory address. Star is an operator that returns what the memory address contains. Right, so the contents of that memory address. On the next line, you can say new is an operator. Is a C++ operator, right? So you say new is a C++ operator, and just a regular operator like plus, minus. New is also an operator. It's just called an English word, but it's just another operator in C++. Okay, new is a C++ operator which allocates and reserves memory for holding the requested object and returns the address. Right, that's all. It allocates memory, reserves it for Matt, and then returns the value saying, all right, this number is where Matt's integer starts. That's what it does. Does that make sense so far, everybody? Okay, all right. Now if you can, now you can see out on line 34, you can print the value, right? You can print the value, see out contents of P, right? See out, or left shift, and then say contents of P, right? Contents of memory location, contents of memory location, contents of memory location P, memory location P. Yeah, equals. No, you need to say equals. Yeah, right now, right, and then left shift. Now you want to send to the what do you want to send to the console? You want to send the contents of P to the console, not P itself. Yes. How do we get the contents of P? P is a memory address. We don't want to print the memory address itself because we've already printed it on previous line. We want to print what the memory address contains. So how do I get the contents of P? There you go. All right, Matt, you typed it and I wasn't looking at the screen. Okay, so you should feel free to talk also so that I get audible feedback. Okay, now if you print it, if you run it now, you'll see that P is this memory address and this is what memory address contains. Right? If you run it now, and most probably it'll have junk in it. Oh, actually, it's initialized. Okay, or maybe it's just that your computer memory has a lot of zeros already. That's what it already has. Okay, so if you had your computer running for a long time and then you do that, you'll probably have junk in that location. So it's not initialized, and so that's what it is. Now you can. How do you set the value? Right? I want to set the value in some random location. I want to set the value of some random location to a number that I want. Okay, how do you do that? So all you have to do is say contents of that memory location equals 7. And then automatically it becomes 7, right? So on the next line, you can say, one more blank line, and say, start a comment there, and say, put the value 7, in the memory location P, right? Which means you're telling the compiler or the CPU, take the value 7. What is the value 7? And so by the way, on the next line, on the next line, you can say for reference, comment. For reference, 7 as an integer is stored in 4 bytes. Is stored past tense, stored in 4 bytes, right? Whose values will be set to, right? WHOSE, right? Whose value will be set to. Actually, you know what? Whose values will be.
I have a kind of a small question. So like, since we're doing this, like we're not, sorry, this is all happening on online GDB and not an actual computer. So like, as far as we're looking at the memory allocation of like online GDB, like, because we're not on an actual, okay.
No, it's an actual computer. It's online GDB
like a virtual.
It's a virtual machine. Yeah, it's a virtual machine. Maybe that's probably that's what I thought originally. I thought the fact that we're getting these big addresses is because it's a virtual machine or a container in some other huge computer, and that's why we're getting these big addresses. So I don't know why. So because because it's same thing happened with Matt's computer also, right? So it's possible that Matt has a huge swap space, right? Huge swap, meaning terabytes. I don't know. Do you have a hard disk that is terabytes big? Yeah, actually, your microphone is on mute, so we can't hear you. So it's unlikely that you have 14 terabyte hard disk.
No, I don't.
But even if you have a 14 terabyte hard disk, I would say it's unlikely for a variable on the stack to be given on to be allocated on swap space
and
on
like
disk, right?
so the swap space and everything being used is it's shown on the activity monitor, right? Like you can see.
Yeah, it actually shows up in the activity monitor too. Yeah, exactly. So that that will be set to. Now we're going to type in the 4 on the next line. We can say on the next line. So start a comment. Yeah, and say what is 7? 7. What is 7 in binary? So 7 in binary is 1, 1, 1, isn't it? 1 plus 2 plus 4. Yeah. Okay. So the 4 bytes are going to be no. Don't type what is 7 in binary. You say 7. You say 0, 0, 0, 0, 0, 0, 0, 0. That's for first byte is all zeros. You remember, an integer is 32 bits. Yes, integer is 32 bits. So the first 8 bits are zeros, all zeros. So type 8 zeros. The next 8 bits, and I put a space there so it's easier for us to space. Yeah, and then again, the second byte is also going to be all zeros. Second byte is all zeros again. The third byte is also going to be all zeros. Yes. And the fourth byte is going to have 0, 0, 0, 0, 0, 1, 1, 1. And that is your 7. Yeah. And the fourth byte is going to be 0, 0. Right. So that is the exact value that is going to be stored in that location, which, it's impossible for us to even count by, incredibly huge location. And we have the power. In the CPU will go right there and say these transistors, that transistor needs to be turned off, made from a 1 to a 0, right? It turns those individual transistors off and on to create that value in that memory location, right? There you go. All right. So on the next line, you can say you want to assign the value 7 to that memory location. So you're going to say star P, contents of P, star P. No, you can just say star P. You say, no, not a comment. You just say star P equals 7. That's it. Okay. That says take the value 7. P is a memory address. P is not, P is a memory address. And this value 7 needs to be put in that memory address. That's what that says. Does it make sense? Well, that's what we say in that comment too, right? On line 36, we actually say that. Take the value 7 and put it in memory location P. That'll happen. Now you take the copy and paste line 34 under that. You'll see that, you'll see what happened, right? Copy line 34, copy and paste that under that line. Now you'll see that, P equals 7. Oh, contents of memory location P equals 7. Does that make sense? So you got to play with this. Now we just did a couple of small experiments, but well, you know what? You don't have to do any more experiments, because in the process of doing stacks, there will be lots of opportunities to play with pointers. But it's very important to play with that the implementation that we're going to do now with stacks, so that you get a thorough grounding in what pointers are. Okay, so if you are all happy with what pointers are and things like that, we'll now go ahead to implement a data structure. This is your first data structure you're going to implement, right? Hey, 2B, you're going to be implementing so many data structures. But 2B, this is the first data structure, unless you've already done Quest 8. In Quest 8, you've got to do this, right? What we're going to do now in class is what you're going to do in Quest 8. However, you'll do a simpler version of what you're doing in class. In class, we're going to use pointers and heap memory. In Quest 8, you're going to be using an array, which is simpler and easier, right? So, so we're going to implement a stack. We can now say, we can start a brand new file. Okay, we say we're going to implement a stack in a new project altogether. Okay, so what you can do is share this, or copy the share link for this thing. And you said return 0 at the end. Return 0 because it's your main, isn't it? Return 0. 0.
Professor, I have a question.
Yeah, sure.
So when we're like doing like the int star p, instead of having it equal new int, could you have it like equal? Like for the example, like we had like int n equals 5, like if could it equal n instead?
No, you cannot do equal n. You see, so int star p equals 5. Is that what you're saying? Can you do
int star p equals
5?
n? Like if we had like int n equals 5, could we do
Oh,
int
no,
star
you
p
can't.
equals n?
Unfortunately, yeah. Unfortunately, you can't. And again, thank you for asking that question. It's very important. Okay, so the reason you cannot do that is because p is a memory address, whereas n is actually a thing. In this case, it so happens, by the way, this is a very interesting question that Namrata asked. Okay, in this case, coincidentally, very rare coincidence, I think, right, for programmers, is that the size of an integer is 4 bytes. However, the size of a pointer is also 4 bytes. Is it 4 bytes? Oh, so you're a 64-bit machine. Is it yours is a 64-bit machine, right? Matt?
Yeah.
It's a reason max 64-bit machine. Okay, all right. So the size of a pointer in a 64-bit machine is 8 bytes, because if you 64-bit machine, pointers will be 8 bytes long because it has more memory. And because the pointers are 8 bytes long, 8-byte pointers, that's why your number is so big. What is 2 to the 8? 2 to the 8 is 2 to the 8 is 4 billion times 4 billion. That's 16. Yeah, okay, maybe that's why it is. Okay, so because your address space is so big, it allocated some big number, but still I don't know why it doesn't map to a physical address. Okay, so if in the older computers, in 32-bit computers, pointers were also 4 bytes, integers were also 4 bytes, you could potentially do, my pointer is equal to an integer, the compiler will catch it and say, hey, this is a different type. This is an address, and this is a thing. How can you say the address is the same thing, right? So Namrata is not the same as 3400 dorm room 5 or something like that. Yeah, that's your address, and that is you. So the compiler will complain. However, if they are the exact same size, you can force the compiler, right, by typecasting and saying, well, even though this is an integer, make believe, think of this as a pointer and take that value and put it in the. It's possible, and people have done that. But it's not good practice. Most of the time, it's not good practice to coerce a type, saying this is the type. I want the compiler to make believe it's a different type and assign. So that's why you cannot say int star p equals n, because n is a different type. P is a different type. You can't assign things that are apples to oranges. Yeah. Does that answer your question?
Yeah, thank you.
Great. Okay. Hey, Matt, clean up the code and say clean up the blank lines 41, 42, 43. Have the return. And then clean up the blank line after return, semicolon after return 0, semicolon after return 0, right? And clean up the blank line after that too. And then this program is good to be, shelved, and we'll start a new one now. Share, you copy that link, and then store it in a file somewhere, so that, when you eventually go to do a Reddit post, you can say, well, we wrote 2 programs. First program was just to play with, allocating and looking at what new does. The second program is where we try to implement a stack data type using dynamic memory. Okay, have you got it copied in a document or somewhere, Matt?
Yep.
Great. Okay. All right. So now let's open a brand new project. You can delete the whole thing. Well, you can just open a new tab. You can open a new tab. Open a new tab. Go to another online GDB. You don't have to kill this, right? So just open a brand new tab in your browser. Right, online GDB again. .com. Yeah. All right, now I can clear off everything and say, well, put a comment on the top, class code for, and we will implement a stack using nodes on the heap, right? And put today's date also somewhere on top so that we know. Implement a stack using heap memory. Okay, great. So here's what we'll do. Why don't we implement a stack of strings? And we'll say a stack of student names, okay? And we'll start pushing the names like Hana, Erica, Matt, Karthik, Elijah, and Namrata. Okay, we'll push these names on the stack and we'll pop them out. And we'll expect to see the behavior of a stack. The last one to go in is the first one to come out, and so on and so forth. Okay, so in order to do that, let's create a hit enter one more time, and say I'm trying to think of a name for this node node object. Say class, and call it. Let's call it stack node. Just call it stack node for now, right? Stack, capital S, yeah, and then underscore. Yeah, all right, that's fine. You have to use camel case everywhere then. Okay. Right now, space, yeah, curly brace. Yeah, and put a semicolon at the end of line 6. All right. Now in here, let's say, do we want to use private and public? Yeah, well, let's use private and so on. Okay. So let's say this is a stack node. So we'll say private. Yeah, private. On the next line, you say string space data. String space data. Okay, now here is the cool part. Okay, and if you've never done this before, this may seem a little jarring, but it is perfectly fine, and you'll figure out what it is. Okay, on the next line after line 8, you're going to say this. Okay, stack node. Okay, stack. No, the name of the class. Stack node. Space. Star. Next. Okay, all right. So this little package here is really powerful, isn't it? Because that is one bead in a necklace that you can form, and your necklace could be as big as your memory allows, right? In fact, this is one node, and you can create as many nodes in the heap. 14 billion nodes on the heap, and you can link them all because you have this special thing called next in there, which next essentially says, well, this is a stack node, but inside of the stack node, you'll find the address of another stack node. That's what it is. Because that's what it says, line 9. What does line 9 say? Line 9 says, inside of this container, I have a variable, a member called next. And what is that member? That member is a pointer to a stack node. That's what it says. Yes? So we have a box which actually points to another box, in addition to having some data. Now, this much, we just need to be 100% confident and comfortable with this before we go on to the next step. Is everybody comfortable with this so far? We have created a box. In fact, we haven't created a box. We have created the template, right? The blueprint for creating a box, which will have data in it and a pointer to another box somewhere else. That's all. Okay, so now let's start main after that, right? So and before we do that, for now, turn that private into public. Okay, we'll go back and do all the access things later. Just turn that into public. Okay, right. So now let's do a main. Okay, now here's what we'll do. So in our main, let's create. Yeah, okay. Oh, Peter is here. Okay, so in our main, here's what we're going to do. Okay, he's trying. All right, here. Okay. So we want to create a here. Go. Yesterday he was here when I was in a meeting with my 2C students. I was really clawing the glass. It was, he couldn't figure out that he can get through the glass. He was just clawing it. And anyway, so yeah, all right. So here, what we're going to do is, yeah, okay. So we say stack node space yeah, stack underscore node space last call it node 1, call it node 1 for now. Okay, call it node 1p pointer. Okay, and put a star in front of node 1p. Put a star and star. There you go. Right, that says node 1p is a pointer to an object of type stack node. Okay, that's all it says. Now, yeah. on the next line, you can say node 1p equals new stack node. Right, semicolon. Right, on the next line, you can say node 1p arrow. Now, so again, this is something you've never used before. Okay, arrow is, yeah, there you go. Right, and don't put a space before the arrow because yeah, there you go. There you go. Right, and what was the variable we had? It's data 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 equals mat within quotes. And then I say node 1p arrow next equals next equals null pointer. Okay, nullptr. Null pointer is exactly the same as the value 0. It's just an alias, right? Null pointer means 0, meaning that there's no more. There's a special address. Okay, now what that means is let's put a comment on the end of line 15. On the end of line 15, yeah, put a comment saying this is the same. This line, this is the same. This is the same as saying. This is the same as saying. No, same as saying. Same as saying. This is the same as, right? Saying, say open parentheses, star node 1p. And then no arrow there. Outside of the parentheses, say dot data equals mat. Okay, all right, exactly the same. And in fact, it is possible for you to figure out it's exactly the same, even if I didn't tell that, right? Then the reason being that that star essentially is an operator that goes and fetches the contents. Yes. So star node 1p is the contents of node 1p, and that's an object. It's not a pointer to an object anymore. It's an object, so I can refer to it just like an object. So object dot. Isn't that how we did it before? Object dot a, object dot b is the contents of the members of the object can be accessed by object dot. Yes. So if you have an actual object, you access using dot. If you have a pointer to an object, you cannot use dot. You have to use dash like that. Okay. Arrow is exactly the same as a dot operator for accessing the contents of an object, except that it is on a pointer. That's all. Okay. Now, let's create one more node. Okay. So now let's create on line 16. Hit enter. Yeah. Okay. Now, yeah. Hit enter. Hit enter. In fact, you know what? We're not yet doing stacks. So let's we'll change the name. We'll change the name from stack node to just say node. Okay, we'll change it later on when we're going to reposition it for stacks. We'll change it to stack node, but now just say node. Okay, also on line 13. Yeah, there you go. There are two, and line 13 also, and 14. Okay, now let's create a few more nodes. There you go, and say node star node 2p, node star node 2p equals new node. You can just do node star node space nodes node space star node 2p, and just another variable. Okay, you can say node 2p, and the p says it's a pointer, not the actual node, and the compiler doesn't care whether you what you call it. You can just call it node 2, but we're putting the p for humans, saying all right, this is a pointer, not right? Node 2p equals new node, equals, just say equals new node, right? And then now repeat the same thing as line 15 and 16, except you're going to say Erica for the first one. Yeah. Arrow data equals Erica. And then, yeah, say Erica. E-R-I-K-A. E-R-I-K-A. Yeah, all right, semicolon. And next line, you're going to say a node 2p arrow next equals. All right, next equals, here's a cool thing, node 1p. Okay, which means we create another node which has Erica's name in it, and its next node is the node that we created before. So we've got a chain with 2 beads on it. Okay, now let's create one more. So you guys, all right, so now create nodes for everybody. Okay, just like this, create nodes, and you got to chain them all up. Okay, I'm not going to say anything from this point onwards until you complete it. All of you can work together. You can call out code. So you need a chain that contains not only Matt now, you need Matt and Erica are already there. This chain should contain Elijah, Namrata, and Hannah. So there's 3 more people you need to add to it. Yeah, okay. And Karthik, yeah, Karthik was also there. Is everybody on board, right? Everybody should be on the same page, exactly. Yeah, all right. Karthik, you good too? Great, great. So you can go and tell, when you're in a discussion. Yeah.
Like keep creating more of the nodes.
Yeah, for every one of you. We need all of you to be in the chain. You can just copy that entire block and paste. Yeah, like what you're doing right now. And then, yeah.
So like the third line, in the little group of 3 lines, that last line is just pointing to like where it started from, because it's like this is creating a new node. What's inside the node is Karthik, and this node is connected to the Erica node. Kind of.
Yeah.
Is this basically what the blockchain is sort of like?
All right, so the blockchain, you're talking about cryptocurrency and all?
Yeah, yeah.
No. It's no. Blockchain is I don't know, right? So it's the way blockchain works is by taking the hash value of an object and encoding that in the hash value of the previous object. So every time there's an object, and then I say the next one goes after that. All the transactions that have happened in the object have a hash value is computed from that and is stored in the currency itself, so that anything you get, you can actually back compute everything and make sure it's all legit. So there's a whole lot of let's not get into the details of that, okay? And it's not, but it's not the same. That's your answer, okay?
Yeah.
So,
But this is like a chain of
it is a
objects?
chain. Yeah, it's a chain of objects. Exactly. Is that it? That's all? One more. Is that all? Namrata, Karthik, Elijah, Erica. Hana. Yeah, Hana. Great. Okay. All right. So now we have a chain. How do you traverse a chain to pick up all the objects? Right? And you can write a nice little for loop. And this is a very nice structure. Okay. And look at it. It's very nice. And now on the next line, after line 36, hit enter. You say, here is the cool way to traverse this linked list. Right? The cool way. Here's the cool way to traverse to traverse. Traverse meaning is just to step through it, right? Traverse the our list or the chain. All right, and we're going to use a for loop. And see, right? So on the next line, say for open parentheses, and here you're going to say node star p, star p. No, node space star p. No. Capital N node, no, capital N for node star p, yeah, equals node 6p, right? Node 6p equals node 6p, yeah, semicolon, and then p is not equal to null pointer. Okay, that's a condition. When p is equal to null pointer, you'll break out of the loop. Yeah, p not equal to null pointer, semicolon. And then to go on to the next one, all you have to do is say p equals p arrow next. That's all. Okay. And that is a loop that will go through your chain, getting one element at a time. After it's processed the element, it's going to set itself. The p is going to set itself to the next pointer. Okay. And so the body of the for loop, in the body of the for loop, you can say, yeah, hit enter. Okay. You say C out, and then you can say p arrow data, and then end all. All right. Now, if you run this, you'll see all of the names, and it'll automatically stop cleanly. Okay, it'll stop cleanly after printing mat. Oh, what's going on?
Oh, do you need STD? No,
that shouldn't have been the. This is a Mac, isn't it? Oh no, you don't have a hash include IO stream.
Oh.
Yeah, or the string at the top, like.
I don't think you need a string. Yeah. No, I don't think you need a, because IO stream uses strings, I think, so it probably includes the string header file itself. Yeah, run it now, and you should see the list of 5-6 names. There you go. Well, you got a semicolon. Get rid of the semicolon. Yeah. There you go. All right. And it's in the exact opposite order that we pushed things in, because we went from the end all the way. Now, if what would be nice is if everybody can confirm that you understand every single word that is in this program. It's a very simple program. If you're comfortable with this, we'll go on to the next step of taking this and turning it into a stack, an actual data type with methods. Let's say push this, pop this, and so on. We'll have an actual abstract data type implemented. But you need to be comfortable with this first. Okay, if you're comfortable with this, we'll do the stack.
I had a question.
Mm-hmm.
So when you have like the star, that's a pointer, right? So if that's like a memory address,
star is not a pointer number. Star is an operator that uses a pointer. So if you use a star, that means you need to give it a pointer. So star p, star node p, no, star node 1p. So star is an operator that takes the pointer on the right, goes to the pointer, gets the contents, and returns it.
Okay, so when you do new node, is that like the pointer?
Yes, new, it will always return a pointer. New says, I've created an object out there and on the heap for you. Here is a pointer that will take you to the object. New returns a pointer.
Oh, okay.
Yeah.
And because we have the star, we have to use like the arrow, and if we didn't have the star, we could just use the dot, like how we usually do it.
Yes, if it was an actual, if you're going into an object and the object is, you're using the actual object, you use dot. Instead of going into the object, you have a pointer to the object, then you need to use arrow on the pointer. Arrow is used on pointers, dot is used on objects. That's the only difference. Does that make
Okay.
sense?
So like node 1P points to like a node somewhere else.
Yes, that's why we had the P at the end. So we
Okay.
added the P saying it's not a node, it's a pointer to a node. So we say it's a P. We don't have to add the P.
Is this like to learn how to use pointers, or like
Yes.
would
This is
it
just how to learn.
would it be a difference like if we didn't have the pointers, like would the node class still work?
What do you mean if we didn't have pointers, the node class would work?
Like would
Oh,
it be
I see. You're saying can we create a stack without using pointers at all?
Yeah.
Yes, that is what you're going to be doing in quest number 8. Are you doing quest 8 already?
Yeah, I did that one. Yeah.
Right. So in quest 8, you're going to implement a stack without using pointers at all. But anytime you're playing with a heap, that's a heap memory, then you have to use pointers to get into the heap.
Okay.
So in this case, we're using nodes, and it's not a stack yet. It's a node, and the node is on the heap. That's why we're using pointers and the star and the arrows and all those things. It takes a while to get the hang of it. Okay, especially even if you've been programming in other languages, just the idea that I got to use a dash arrow and all these things. It just practice. Okay, you have to get used to it. But it will be. I can guarantee, 100% guarantee that once you use it for, let's say, a week or so continuously, after that you won't even be thinking about it. You'll automatically know this is where all these things will become second nature to you. But in the beginning, it kind of looks jarring. Hey, there's a new thing that I'm going to use. In fact, it's new NAW, right? So all of those will be jarring in the beginning, but it's very simple.
How come we don't use new for next? How come we don't use new for next?
Yeah. Because we're using new on the container of next, which contains it's right. Next is contained inside of a box called node. We define something called node, which has two things in it. Yes.
Yep.
Node has two things in it: data and next.
Yeah.
So when I say give me a node, give me a new node, that new node already has a new new data and new next in it. So when you allocate a new node, it's automatically allocated both of the things inside of it. So you don't have to say new next or new data.
Okay, so this creates a new object.
Not where you have a cursor. Where you have, there you go, line 20, for example. Line 20. That new node creates a brand new node. Or on line 16, right? Line 16 creates a new node, and that node already has both of those things inside of it, data and next. So you don't need to do new next in there. Does that make sense?
Yeah. Oh,
like
okay.
I said,
That's why you don't have to
working with
do new
pointers.
data. Oh, I see.
Yeah. Now the thing is, one of the things is when so you ask these questions, Namrata asked these questions, and now you know the answer, so you understand. So you essentially understand now, right? You understand that wow, that's why you don't do a new next and all. Yeah, but understanding is not enough. Unfortunately, lots of students will stop at understanding and say, okay, I know how it works. No, right? You need to understand it and also practice it so that it's internalized solidly. And so so you need to it will be jarring for a little while, because people don't play with heaps, especially and so in other languages, right? So it's good to know this.
So far this is a heap, like
everything you say, when you say new, you're getting stuff from the heap. Anytime you say here, give me a new thing, it gets it from the heap. If you don't say new, then it's already on the stack. So right, so heap memory is accessed using the new keyword. Does it make sense?
Yeah.
Great. Okay. All right. So now let's see. Shall we do
wait, one more
you
thing.
Tell me what.
Wait,
Go
question.
ahead.
So for the loop, just in kind of like plain language, right? So where that node star P, you're saying it starts at the value that node 6P has?
Yes.
Right?
No, it starts. No, I'm saying it starts at the value, which is an address that points to node 6P. So P is not node 6P. P, when you start, When you start, P is an address that points there. And inside the loop, the address is going to get reassigned to the next one. So the address keeps on changing.
Okay.
The loop changes the address repeatedly, not the actual object.
And so this address of node 6P is larger than the other ones? Because like the stopping point is P doesn't equal 0 because null pointer was like R0, right?
No, the stopping point is 0. The stopping point is 0, isn't it? There you go. So
cool, because it says not equal, like the exclamation equals null pointer.
yeah, that's a stopping point.
Yes.
No, it's a stopping point. The middle thing in the for statement is a stopping point. When that is true, exit the loop.
Right. Oh, and so null pointer isn't 0?
No, null pointer is 0. Oh, hang on.
Oh, shouldn't it be equal 0?
Oh, no, sorry, yeah. If it basic for loop syntax. Okay.
Yeah.
It says that middle condition, keep doing the loop as long as the middle condition is true. So if P is not a null pointer, it'll keep in the loop. At the moment that P becomes a null pointer, it'll exit the loop. So if it is not equal to null pointer, go into the loop. If it is, that's what you do even for I equals 0, I less than 10, right? If you write a regular loop, it'll be in the loop as long as I is less than 10. As soon as I becomes 10 or greater than 10, it'll break out of the loop. Yes.
Right. Okay. Yes. And so then
exactly the same here.
And then as it increases, P
doesn't increase. Doesn't by the way, it doesn't increase. Right, because the first node could be at a memory location 50. The second node could be at memory location 25. Who knows? So the addresses may not increase. We just know they're linked in that order. That's all.
Right. And so like for the next part, like the next part of the loop, like P equals as like, and then P is pointing to the next, right? Because then it'll go like each node's next is like the previous node, right? So it'll just.
It's the next node. Yeah, it's not the previous node. It's just the next node.
Or like next. Oh yeah, but like it's like each like node 6P that next is node 5P, right?
Yes. The node 6P dot next is the address of node 5P. Well, it's the address of node 5 and node 5 because node 5P is the pointer to node 5, isn't it?
Yeah.
Node 5P is the pointer to node 5. So node 6P next is node 5P, which is a pointer to node 5. And node 5P next is node 4P. Oh, node 4, yeah, is it? So it goes like that. And that's why it takes a little while. That's why it takes a little while to get the hang of a for loop that is based on pointers. Because you're all totally comfortable at this point with writing for loops that are based on integers and other things. Yes?
Yes.
But using for loops that are based on the conditions that are exit conditions that are based on pointers is a little hard. And even if you get completely comfortable with this, right now, even yesterday in CS2C, some students were having a problem in a for loop, or I don't know if it's a for loop, in a loop which wasn't breaking, which wasn't exiting based on a pointer check, right? And so even if you know this completely and understand it and have practice, you'll still run into situations where you have some condition based on a pointer, which is not null, is not breaking at all. It's infinite loop, and
that's caused a memory leak.
Causes memory leak, or memory leak in a better case. In worse cases than that, it might cause your program to crash. Yeah, and it's like that. So that is practice. Practice is a lot. Practice is a lot. Come up with your own loops. Write lots of loops. But writing loops, especially while loops, while loops are even harder, and that's why I always in CS2A always try to use for loops as much as possible. Although you shouldn't be doing that. You should be trying to play with while loops also. But for loops generally are less chances of have less chance of being buggy, because in while loops things could happen at different places, and you may change something and forget it, and that's why it's play with pointers using while loops too, and saying, hey, while P is not equal to null, I'm going to do this. And in fact, why don't we write the same thing using, go on to line 44, go to line 44, go to line 44, hit enter, one more enter, and put a comment there saying we will write the same loop as above using while. Okay, how about I don't do this? Okay, why don't you guys do this? Are you comfortable with doing this? You got to use exactly the same behavior, exactly the same as a for loop, but do it using while loops. Can you guys do this or not? Raise your hand. Do you want to do it?
Yep.
If you don't, I can walk you through this too. But raise your hand if you think you're comfortable with implementing exactly the same thing using a while loop. Well, Matt's already trying to do it, which means that he has raised his hand. Matt, you're comfortable with doing it, yes?
Yes.
Okay, all right. Okay. I'm not going to say anything, okay? Even if you make mistakes here, I won't say anything. Let's look at the time. What time is it? What is it? What is it? Oh my gosh, it's 10 o'clock. We didn't get a chance to implement, but yeah, but this is important. I think this is more important than actually implementing stack. So go right to the top of the file and erase that line in the comment that you said, implementing a stack. We'll implement a stack next class. That's fine. Okay, we got time to do that. But today we're just playing with implement. What we're going to do is play with nodes, play with node chains. Implement a node chain using heap memory. Okay, I think that's better. And after this, I think we can call it a day because we've done quite a lot of stuff. Even though it may not seem like a lot, this is a lot. Based on my experience from previous CS2A classes, this is a lot, even though there's a lot, not a lot, because it's doing pointer manipulation and it requires a lot of practice. So take apart, I think after this class, before, whenever, take 4 or 5 hours of time. Okay, set apart 4 or 5 hours of your time just to play around with allocating stuff on the heap, using next pointers, making chains, making huge chains, traversing these chains, going from here to there, and then going into a chain and removing a link. And in fact, with well, we won't do that in class because you got to do that in quest 9. Quest 9, I bet that if after you complete quest 9, you can talk about pointers if someone wakes you up from sleep, right? So in the middle of the night, someone says, hey, you know what, I'm going to do this pointer, what's going on here? You say, oh, you just need to do that, okay, and go back to sleep. You'll be that comfortable after quest 9, because quest 9, you're going to be throwing pointers left and right, everywhere. And you'll be given a long list. And one of the mini quests will say, in this list, go and remove the node which is at position number 7, right? It's not the first node, not the last node. You got to go and remove some interior node. How do you do that? And so you got to do very carefully, right? Very carefully is the answer. And you got to go all the way, unlink that, and that takes a little bit of finesse. All right, so try and do that on your own before you go to quest 9, and then quest 9 will be a breeze after that. Hey, Matt, that is really cool. That is really cool. So yeah, well, it looks like, well, if you run it now, I'm pretty sure you'll see the, well, before you run it. Oh, you already ran it?
Yeah, I already ran
okay. It works. Okay. Does anybody have any questions on what Matt just did? No, is everybody comfortable with pointers and linked chains and so on and so forth? Excellent. All right. So here's what my plan is for next class. Okay. Next class, what we're going to do is this node thing is going to have node and exactly the same node. However, we'll also implement another class called stack. The stack is going to be a linked list of nodes. That's all. Okay. It'll start off with nothing in there, null pointer. That's your empty stack, right? When you push the first thing on the stack, that's going to be the first node. Push one more thing on the stack, that first node becomes the last node. And the first node is on here. Okay, you push one more thing on the stack, these two guys go here, and third node. So third node is always the first node, and it links backwards. And the last node there is going to have a null pointer because that's the one that was a node that was created first. Yes, so you're going to keep pushing on the stack, and when you pop off the stack, all you have to do is just take the first node, remove it, and take the and say the top of the stack is not the first node anymore. It's the one that was pointing to. That's all. Okay, so that's the thing that you have to remember is at the end, before the return statement, let's put a comment, right? Put a comment there, a blank line and then a comment. Yeah, right. In the comment, say whenever we work with heap memory and allocate resources using new, we have to remember to deallocate them. Yeah, on the next line, you can break it into the next line. You see that vertical line is that 80 column limit. Remember to release it back to the operating system. Remember to release them back to the operating system. Release them back to the OS. right? So let's write a really quick for loop that will do the release operation. Okay, and it's not, it's so the releasing is not as simple as that, and you'll see why. Okay, so let's say for node p equals node 6p, for node p equals node 6p, node star p, no, node star p, sorry, node star p equals node 6p, same as before. You put the same thing as before. Oh, you know what? We're going to use the while loop. We're going to use the while loop like, yeah, copy what Matt wrote on 47 to 47. Yeah, put it there. Put it there. Yeah, get rid of the for statement and paste what you did. Right here, you're going to say this, right? While p is not equal to null pointer, what you're going to do is, all right, inside the for loop, inside the while loop, go into the while loop. The first statement, right? There you're going to say node star q equals p, node star, or let's not call it q, right? Call it node star, node to be deleted, node to be deleted, node to be released, node to be released, node to be released. Equals p, semicolon. No, actually, hang on just one sec, okay? Trying to node to be released. Wait, no, we want to release it. So what we'll do, all right, yeah, right. Node to be released next. Call it node to be released next. Call it node to be released next. Equals p arrow next. P arrow next. No, not underscore. It's got to be dash. All right. Now on the next line, you're going to say delete p. Okay, delete p. Now p is gone. However, we still need to go to the next node. But the next node was stored inside of p. If p has been released, you don't have any way of getting back to that node. Yes. However, we anticipated that, and before we released p, we took the next and stored it somewhere. So now all we need to do is on the next line. On the next line, you say p equals. No, not there, not there. After your get rid of the cout. Get rid of the cout. Right? Yeah, that p equals p arrow next. Change that p arrow next. No, change that p arrow next. Change that p arrow next to what is it? Node to be released next. Node to be released next. Yeah, there you go. Right now, yeah, that is it. And you can close it off. You can remove the blank line. You can really remove the blank line. Remove the blank line under it. And in fact, you can also put a cout in there before the delete. Before the delete. Say cout about to release. Node stored at. Node stored at, right? And then left shift p after that, and L, left shift p, and L. Right now, if you run it, it'll actually go and delete all those things. Okay, it'll run it now.
You have to comment this, right? Comment this out.
No, you can. No, you don't have to. Because it's going to print. It'll just print some junk before, right? It'll print that. Yeah, there you go. Oh, wait a sec. Node star p equals.
Oh, yeah, it was a read.
Oh, that's why you said you got to. I see. Thank you. No, that means you got to comment out the whole block. You got to comment out the whole block, not because you're using p and without declaring p, it'll cause errors. Make that a block comment. And comment out everything from 46 to 51. Oh, okay, cool. That's great, right? So if you run it now, you'll see that it'll actually, right, about to release. So it actually released each one of those. Now, if you didn't do this, if you didn't hang on to that. Now, in fact, what you can do is after on line 62, try to print the contents of node 6p data, right? Print the content, cout on the next line. Not there, after the while loop. After the while loop. One more now, and put a comment there first. Put a comment there. Comments there. The following cout the following cout statement might crash the program because it is accessing memory that does not belong to us anymore. Yes, because we've released the memory and we're going to try and access it after releasing it. Okay, now say cout, cout, and say node 6p data equals, and then say node 6p arrow data. Arrow data and endl. And you can put a tag also before endl, and put a tag saying before the first one, say node 6p arrow data equals within quotes. Open a quote. No, but after the cout, left shift a string that says, left shift a string after cout. After on line 65. There you go. Yeah. You can say within quotes, you can say node 6p's data equals node 6p's data equals. So no, node 6's data, node 6's data, node 6 data equals node 6's data equals. Not data, not. And also it's not node 6p's data, it's node 6's data, right? Node 6p is a pointer to node 6. But that doesn't contain the data. Node 6 contains the data. Yeah, thank you. Right. So now if you run this, it might potentially crash your program saying, there was an error. You tried to access something that didn't belong to you. Run it. Semicolon. You're missing a semicolon somewhere. Oh no, you're missing a left shift before. After that first string, node equals, yeah, left shift. Well, okay. If you run it on your own computer, I'm pretty sure it'll crash. Okay, this didn't catch the error, and it's because it didn't catch the error because it is impossible for a compiler, the runtime system, to monitor all memory locations. It monitors one special memory location, that's memory address 0. That is why when you're programming with pointers, it is helpful to set pointers that pointed to a real object. After you release the object, you set the pointer to 0 or a null pointer. That will guarantee that it will flag. In fact, if you go to line 60, go to line 60, go to line 60, and actually you can't, right? Well, yeah, it's you can't. So it's not able to catch it because it's pointing to some address, and it was the runtime system wasn't monitoring the address for changes and all. So it should have crashed your computer at that point, right? Not your computer, that program should have crashed because you're accessing memory that didn't belong to you. And somehow online GDB is letting that fly. Anyway, so that is what it is. I hope this has enough information for you to noodle on. I'm not seeing a great deal of activity outside of class in the forums, and so I don't know if you're devoting enough time outside of class to these things. But now is the part that we're getting to the difficult parts of C++. So this is the time when you need to spend more time on the topics. So please do noodle on this, think about it, have discussions with your classmates, post things, interesting things that you create on the Reddit. So all be really, really good practice as you move into quest number 9 and beyond. Do you guys have any questions? Next week we'll implement a stack using nodes just like this. Okay. And the week after that we'll implement a linked list and a game using linked list. Okay. So I'm thinking of that Wheel of Fortune game that we did in a previous quarter. But I think by the time we get to this, I would have thought about it a bit more, so it'll be more feasible. Well, actually, we managed to get it to run last quarter too, but maybe we can do it with more bells and whistles this time. Maybe we'll do it with a bit of animation with the screen thing that you've created before. Wheel of Fortune with animation and linked list for for good measure. Everything's thrown in.
Could we also because we did it using the public data? Could we later make it?
Yes, yeah, totally. Yeah.
Then...
Yeah, that's what we'll do next class. Okay. Next class, awesome. What we'll do is we'll take the node and we'll make them, some private. And then once you make them private, you need constructors now, because you can't constructors and setters and getters. We'll put them in, and then we'll have a stack which will definitely have private pointers in it, because the stack will not allow you to access anything, right? So we'll have private and public and scoping rules and everything taken care of there.
Sounds awesome.
Yeah. I think this is the exciting part of this class. And unfortunately, lots of people have dropped off and no, they're still in class. They haven't dropped the course, but they're not turning up to lectures. And it's a pity because this is a time when students actually have to attend and learn. Because the earlier parts you can learn on your own. This requires practice and working with other classmates to really nail down proper. So yeah, please pass the message on to as many people as you can. And I hope to see you all on Tuesday, and have a great weekend. Continue coding with this, and see if you can come up with something that's interesting, entertaining, and fun, and sure, do share those things. Okay, I look forward to that. All right, thank you for your time and patience, Matt. Especially thank you. You were actually typing ahead and helping this happen, because I can see that this whole thing we managed to do only because you were on the ball and getting things done. So thank you again.
Should I put it in the chat?
No. You should share both of those links on Reddit. Share both the links on Reddit. And also, don't just share, here are the 2 links, okay? Some people are doing that. Oh, here's a link we did on class. Karthik especially did that. Where's Karthik? Right? Karthik, when he posts a link, he basically just says, here's a link, right? Now, don't do that. Okay, so post a link and also say this, we did this, okay? And so people, before they click on the link, they already know what they can expect when they go into the program. All right, thank you all, and I will look forward to seeing you on Tuesday. Okay, and by the way, any of you, if you're planning to be here next quarter, okay, it's spring quarter, if you're planning to be enrolled in courses at Foothill, if you're enrolled in at least 12 units, okay, 12 units at Foothill, can be De Anza, all 12 units at Foothill, and you've completed all 9 quests, you should apply. I think I have 2 more weeks to tell the STEM Center, okay, to apply to be an embedded tutor in CS2A. I think the pay is reasonable, okay? It's better than minimum wage, better than they pay at McDonald's, right? Better than minimum wage, and you can get a decent number of hours each week to tutor, and at least one of those hours is easy because 4 hours per week you can actually attend class, attend my 2A class, which you've already done. For next quarter's CS2A students, you're going to be present in the back like a tutor, and if students have any questions or times when I disappear, you can help out. So that counts for 4 hours automatically. 4 hours of pay. On top of that, I think they expect you to hold 1 or 2 hours of tutorial sessions where you can talk about any topic. You can take any topic in LOSAF and say, I'm going to offer a tutorial for everybody turn up, all the students turn up, and you teach, right? And you can do your own teaching. It's a very nice experience being a tutor, okay? Because I don't know, it's fun. Talk to Walter Bergstrom, okay? He was a past tutor in CS2A. If you want to be, you have to have completed the course, which you are, all of you here, definitely going to complete the course with a good grade, and 12 units, and consider being a tutor, okay? And it'll be fun. It'll be fun. All right. See you later. Bye.